everyone, thanks so much for joining me for this 1,000 subscribers special. From the bottom of my heart, I can't thank you all enough for the support you've given me over these past 11 months since I started this channel. I deeply appreciate all of you that watch, subscribe, comment, and like my content. I hope that it has been educational and at least occasionally entertaining, and that I've managed to deepen your understanding of evolutionary biology. For those of you that are new here, my name's Zach Hancock. I am an evolutionary biologist who specializes in population genetics, phylogenetics, and genome evolution. I received my PhD in evolutionary biology from Texas A&M University, and I'm currently working as a postdoctoral researcher at the University of Michigan, where I help to develop statistical models for analyzing spatial genetic data. This channel exists as a sort of creative outlet for me to share my opinions and thoughts on evolution, often pitched in an educational way, as well as the history and philosophy of science, all mixed in with the occasional pseudoscience debunking. My normal target is creationism, though I occasionally address claims from race realists and transphobes. I have struggled in the past few weeks since hitting 1K subscribers to figure out exactly how to celebrate this milestone. I know many channels take a kind of retrospective look at the channel, discuss some personal motivations, and give some indication of where they see the channel going. I'm gonna try to follow that general tradition, but with just a slight twist. For this 1K special, what I've decided to do is provide a sort of comprehensive lesson on evolutionary biology with a particular eye to addressing creationism and so-called intelligent design. Along the way, I'm going to mix in some history and philosophy of science such that this video will sort of integrate all the major themes that I've touched on in this channel. My goal here is that the video will not merely be for those who have watched the channel up until this point, but it will be relevant to the wider conversation about evolution and creationism. This approach will likely make this a longer video than usual, so feel free to jump to the sections that interest you the most. While I believe this video will be interesting and useful for people of all philosophical and theological backgrounds, I will be speaking directly to the arguments put forward by Christian creationists. If you happen to be a creationist watching this video, welcome. In the words of the great carcinologist and evolutionist T.R.R. Stebbing, the range of topics embraced in the present volume should at least teach those who are willing to learn that the whole subject is a great one and worthy of attention. It cannot be disposed of by caricaturing. It cannot be settled in deference to any religious prepossession. It must be examined with open eyes and with the full candor of mind which great subjects demand. With that being said, thank you all once again for your continued support and for helping this channel reach 1,000 subscribers. I want to begin with my own personal journey to evolutionary biology, and this will ultimately guide us into the philosophy of science before delving into evolution itself. I want to begin with a confession. As a youth, I was not interested in science. I performed poorly in all of my biology classes. I hated algebra and geometry in grade school, and was just bored to the gills in chemistry. I think that this is partly due to the influence of my mother. She taught high school English and had a deep love of the classics, especially the romantic writers like Emily Dickinson, William Wordsworth, Charles Dickens, the Bronte sisters, and Jane Austen. Children want to relate to their parents. They want their attention and approval, and so sometimes subconsciously will adopt the interests of their parents. This is not to say that I had no natural interest in literature. I definitely did, and to this day I often joke that my ultimate career goal is as a novelist. Science is just a stopgap on the way to the bookshelves. But these writers all shared a disdain for the concept of scientific progressivism. In many ways, the Romantic era was a reactionary movement against the scientific revolution started by Copernicus, Galileo, and Isaac Newton. Their views are best summarized by Wordsworth's 1798 poem, The Tables Turned. Sweet is the lore which nature brings, our meddling intellect misshapes the beauteous forms of things we murder to dissect. To the Romantics, truth is a feeling. It's a state of mind, a sort of oneness with nature and with the mysteries of the cosmos. Science, alternatively, views in mystery only opportunity for discovery. It acts to unweave the rainbow, in the words of John Keats. Poe famously asked, "Why preyest thou upon the poet's heart, vulture whose wings are dull realities?" This detestation of the dull realities of scientific pursuit from the Romantics bears in it a natural bedfellow of creationism. Every Christian is privy to the dictum, God works in mysterious ways. The insinuation here is that there is that which man can never know or understand. There is inherent in reality something mysterious and inaccessible to us as mere mortals. My mother was not literate in science, but she was a creationist, and she raised my sister and I in that tradition. Being from the South, I was reared in the Southern Baptist denomination and was baptized before I was 10 years old. I became deeply religious during my preteen years and traveled with a revivalist preacher for a time, knocking on doors, spreading the proverbial good news. I once spoke in front of a crowd of thousands in Baltimore about my experiences as a door-to-door evangelist, and people found my devotion to the cause, despite my young age, a kind of endearing quality. Despite my devotion, I was a precocious child. I was deeply curious and inquisitive, and I would often press my pastor or my mother on theological questions that didn't seem to my young mind logical. Over the years, I became increasingly dissatisfied with what I found to be progressively hollow answers from the church elders. I should remind folks here that this was the 1990s and early 2000s, before the internet was widely available. In my hometown, we didn't have dial-up until I was in high school. You either found a book in your local library or you tried to learn from those who you felt knew more than you. That is, you asked questions. But there seemed to me to be two sources of authority. There was the biology teachers and the textbooks they taught from in my public school that made pronunciations in one direction, and then there was my pastor, my years of Sunday school and Bible camps, and what seemed to me to be a plain reading of the Bible that contradicted them. My young mind was truly torn. I remember vividly a formative moment in which a biology teacher drew a line on a chalkboard that was meant to represent the entire history of the universe. He gave each of us a piece of chalk and told us to approach the board and mark where we thought humans emerged. Of course, I knew what the textbook said. Humans had evolved very recently, and so I should put my mark towards the end of the line. But in Sunday school, I had learned that the Bible clearly stated that man was created on the sixth day, and so must be somewhere at the beginning of the line. Everyone in my class marked near the end. A few goofballs guessed in the middle, but I walked right up to the board and put my X near the beginning. For many years, I looked back on this moment with pride. I vaguely remember telling my pastor about the incident and him patting me warmly on the back. To my family and church community, I had chosen the correct source of authority. Today, I'm embarrassed by this incident, and with a similar incident I had in my first semester of college. The professor I had was abrasive and told all the students forcefully on the first day of class that evolution is just a fact, deal with it. I was immediately turned off. I eventually dropped out, but before I did, I wrote an extensive essay, totally off topic, on the last test that I took. I knew I wasn't going to come back to class, so I explained to the professor exactly why I thought science was bastardizing the human experience and cheapening the mystery of God. These incidents must seem odd, given the ultimate trajectory my education would take. And there's no one moment or incident that can claim responsibility. The gradual erosion of my own faith in the authority of the church began first as a result of my own study of the Bible. I found inconsistencies in interpretation, including a view that I developed that the book of James undermined the Baptist claim that faith alone was required to enter into heaven, relying on John 3:16. The issue came to a head when the church sent out a call for volunteers to write monthly devotionals for a calendar, and I submitted a piece focused on James 2, which states, quote, "Faith without works is dead." I emphasized in my devotional submission that faith alone isn't enough, but that the Christian is required to also display works. The church elders, without my permission or notifying me, heavily edited my devotional to fit their own perception of the book. After the affair, I left the church. I became convinced that I could discern God's message myself straight from the Bible. At the same time, I was given a copy of some classroom materials from the Discovery Institute, a creationist think tank, that they had developed to promote intelligent design and Michael Behe's idea of irreducible complexity. If I'm to be honest, and what else is a 1K subscriber special about, if not personal honesty, I rapidly lost interest in these more academic, theological concerns upon entering high school. There emerged for me a series of much more interesting distractions, namely girls, drugs, and rap music. I know, sorry, I was a teenager once too. For about 10 years, from high school until my mid-20s, I was consumed in a lifestyle that generated for me enough distance from my evangelical upbringing that by the time I walked away from it, I could return to the question of authority with clearer eyes. My slate was cleaner, if you will. Not blank by any means, but it was less cluttered. I did return to the question with at least some inclination that atonement was needed, that I had done irrevocable damage to myself and others, and that only through grace could I put myself back on my feet. But it wasn't grace that returned me upright. Instead, it was the persistent challenges of my friends that I had made along the way. My obstinate, pig-headed friends that loved to argue and knew that I was a person of strong conviction and would engage. They challenged me to learn more, to dig deeper into my own preconceptions, which I thought would reveal God to me, but instead just led me to dead ends, one after the other. Every argument my pastor had told me, every assurance by my Sunday school teachers just crumbled the harder I dug, and in the end, they all offered the same unsatisfying platitude: just have faith. God works in mysterious ways, so why prey upon the poet's heart with your dull realities, O ye of little faith? The sentiment is condemned in Cormac McCarthy's 1985 haunting novel Blood Meridian, in which the character of Judge Holden explains, "The man who believes the secrets of the world are forever hidden lives in mystery and fear. Superstition will drag him down. The rain will erode the deeds of his life. But that man who sets upon himself the task of singling the thread of order from the tapestry will by the decision alone have taken charge of the world, and it is only by such taking charge that he will effect a way to dictate the terms of his own fate." Returning to university when I was 26, I initially studied history and literature, but would eventually switch to biology. By this time in my life, I was dedicated to trying to figure out what is true, and how I could know something to be true. At the same time, I was disillusioned with systems of knowledge that claimed to have some unique access to ontology. Instead, I wanted an epistemology that didn't claim to know things, but rather provided a systematic methodology for discovery and assessment, a tool for delineating things likely to be true, all the while recognizing that truth, with a capital T, is ultimately inaccessible to us. that, in my mind, would be a system capable of self-reflection and correction. One that would not become swept up in its own claims and biases, and would instead follow dull realities wherever they led. Despite the way I've framed this, science was not my first choice. I searched other philosophical disciplines and even religions in my quest for an internally consistent and practical epistemology. As I said at the beginning, I was initially skeptical of science from the very beginning, both because of my upbringing and my readings with the Romantic writers, as well as my experience in Sunday school. But a series of books changed my perspective on this. The first was Richard Dawkins's The God Delusion, which I read at the behest of a friend of mine. The book had exploded in popularity at the height of the Iraq War and coincided with the rise of the so-called New Atheists, increasingly combative anti-theists that saw religion as a plague on humanity that needed to be snuffed out. If this seems odd today, you might just be too young to remember that the 9/11 attacks and the panic that sort of swept through the world. Christians interpreted the attack as an assault on their religion. Atheists interpreted it as religion in its ultimate form, destructive and chaotic. As is typically the case, both of these views were wrong, and the 9/11 attacks were driven by geopolitical frustrations that emerged as the result of the fear of the spread of Western capitalism and consumerism, coupled with interventionism in the Middle East. But nuance doesn't make headlines, and nor does it sell books. The God Delusion is not a good book. But it did sort of finger the pulse of the world at the time, and for me, it promoted science as an antidote to religion. I wasn't necessarily looking for an antidote to anything, but it put science on my radar. So I went on to read The Ancestor's Tale and The Greatest Show on Earth, as well as Stephen Hawking's A Brief History of Time, and eventually Stephen Jay Gould's A Wonderful Life and Ever Since Darwin. At the same time, I was taking my first college biology courses and opted to take the course for majors despite not being a biology major. My mentor was a man named Dr. David Allard. He was a limnologist trained in the systematics of water fleas, these tiny freshwater crustaceans. He was a Methodist and an active member of his church, along with being an avid supporter of evolution. We would have lunch together many days and discuss politics, religion, science. He gave me several books, including Michael Roos's Can a Darwinian Be a Christian? And Ken Miller's Finding Darwin's God. I credit him for sort of tempering my growing animosity towards religion during those years when I was consuming Dawkins and Sam Harris, Daniel Dennett, and Christopher Hitchens. He always had these careful, nuanced takes that made the so-called four horsemen of New Atheism seem like hotheads that hadn't much training in history or philosophy and were more interested in polemics than discourse. A kind of curious tradition started for me during that time that continued throughout graduate school. Little by little, I became disinterested in religion entirely, which perhaps paradoxically led me to also abandon the label of atheist altogether. In large part, this coincided with me learning more about evolutionary biology. It simply didn't need defending. The better I understood cellular mechanisms, genetics, embryology, and morphology, and comparative anatomy, the clearer it was to me that there was nothing speculative about evolution at all. It was ultimately fundamental to the life sciences. Whether or not you think Dobzhansky's maxim hyperbolic or not, there is inherent truth in the statement that nothing in biology makes sense except in light of evolution. Why bother with creationism, the authority that had tortured me for so much of my youth, when it was so thoroughly unnecessary as an explanation for biological diversity? We've been going on for some time now with this personal tale that now is perhaps a good moment to sort of stop and reflect. Perhaps the central reason for my ultimate rejection of what I had been taught my entire childhood was, in the end, education. I simply learned more. Hence, for me, a major theme in this channel is evolution education. I contend that most people that reject evolution do so from a position of ignorance of the subject, as I did. I state this because when I listen to even professional creationists speak, they make the same basic mistakes. I recognize this may be from ignorance or be deliberate, but I choose to believe people aren't lying to support their position. But there is a component of this that is not merely a function of knowledge. There is, of course, a serious impediment that is foundational. We are all disputing facts in different ways, arguing from different presuppositions, and these cannot be ignored. With my own personal journey to science in mind, let's now take a step back and talk about Weltanschauung, our worldviews, with a special focus on how they develop from our initial presuppositions. The inspiration for this channel came in 2021, during the height of the COVID pandemic. I had just accepted a postdoctoral position at Michigan State University and had moved from Texas to Lansing that winter. Since the world was on lockdown, no one was fraternizing, and establishing a community in a new city was impossible. I was forced to turn to virtual communities. These included gaming communities and Discord groups, as well as YouTube communities. It was during this time that I discovered the evolution versus creation YouTube debate scene. First on the channel Standing for Truth, hosted by Donnie Badinsky, who I'm sure many of you are familiar with. The first debate I watched featured the disgraced creationist Ken Hovind. When I was young, Hovind was a household name among evangelicals, but after he was convicted of tax fraud and spent 9 years in prison, most evangelical circles distanced themselves from him. I should note here that Hovind was also convicted of domestic violence in 2021 and harbored a known child abuser at his park that specifically advertises to children. Over several months of watching these debates, I found they came in one of two flavors. One focused on so-called scientific arguments for creationism, while the other focused on battling worldviews. However, these were exactly the same disputes, because despite creationism often adopting the language of science, it rejects most of its presuppositions. Hence, we cannot, strictly speaking, have a scientific debate about evolution and creationism. I'll explain why shortly. Worldview is a loaded word that incorporates one's experiences, culture, beliefs, and moral systems. The concept that evolution and creationists differ simply by a worldview is an attempt by some larger creationist agencies, most notably Answers in Genesis, to shift away from disputing facts and rather pitting man against God. Indeed, this is the tactic of many creationists on SFT's channel. After all, the argument is easily won if you simply construct an argument in which man's wisdom is compared to that of a definitionally all-knowing deity. These sorts of arguments always begin with a predictable line of questioning, such as, how do you know you're right? Or, what is your foundation for knowledge? These are traps meant to expose you as a mere fallible mortal, and that your very ability to utilize reason and logic must itself come from something else. God's existence is the presupposed prerequisite. These rhetorical tricks are tiresome and dishonest. None of us, whether Christian, Muslim, atheist, whatever, can escape the problem of hard solipsism. That is, beyond our own minds, we must presuppose an objective reality exists. As a presupposition, anyone is free to reject it. It is assumed without evidence. Creationists and evolutionists alike share this presupposition, that there is an objective reality. From here, however, we can begin to diverge. Scientific epistemology presupposes further that this objective reality is governed by natural laws and forces. For example, that the motions of gas particles in a vacuum can be modeled under the ideal gas law. Or that there exists a force of nature that we call gravity, that describes the attraction between two objects, the strength of which is dictated by the object's mass. Creationists accept at least some of these. The acceptance or rejection of any law or force of nature, as far as I can tell, is a function of how strongly it disagrees with their interpretation of the Bible. The valence theory of electrons doesn't lead to a rejection of the resurrection, but there are core concepts in nuclear physics, such as the constancy of nuclear decay, that violate their preconceived timeline of the universe and hence must be rejected. And here we see that they've adopted a presupposition that science hasn't. That is the presupposition of the inerrancy of Scripture. We know this presupposition exists because which natural law or force they reject or accept is contingent on its relation to the Bible. Hence, before we've even presupposed that the material universe is governed by natural laws, creationists have snuck in a biblical presupposition. We have already diverged from the outset. We can agree only on an objective reality. From there, the presupposition of the Bible precludes further investigation. We cannot establish any further principles of epistemology or logic due to this immediate divergence. I want to stress here that the biblical presupposition, while stated as a single entity, is itself an extensive claim about the nature of reality, history, politics, nature, and God. It is a gigantic philosophical burden to laden any evolutionist with, to try and engage honestly from first principles when you must, on the outset, presuppose such an extensive worldview. So this may be where some of you get off the train. If you're unwilling to set aside your biblical presupposition, then we cannot agree on anything past objective reality. We can discuss scientific topics all we'd like, but it will ultimately be unproductive because your foundation assumes far more from the outset than any interlocutor can reasonably be expected to entertain. However, if you're willing to set aside this presupposition for the purpose of argument, or you contend that you have arrived at this biblical worldview not by a faith-based acceptance of the Bible as the inerrant word, but rather through an evidential investigation, then we might be able to progress. Either way, please be aware of the bias we've started with and try to not let it color your view of the science to come. So we stand at two presuppositions. One, that objective reality exists, and two, that the material universe is governed by natural law and forces. Science also presupposes that these natural laws are knowable by man. That is, humans have the intellectual capacity to understand them and discover them. Again, this may or may not be true. The Romantic poets certainly doubted it. But any scientific endeavor cannot begin by stating, "Well, I hypothesize we aren't smart enough to figure this out." Lastly, for any discovery of science to be meaningful beyond the immediate, we must presuppose that the natural laws aren't arbitrary, but act the same everywhere. The strong nuclear force behaves the same on Andromeda as it does here, and that these forces will continue to be the same irrespective of the time of observation. That is, if we can understand how a natural law behaves in the present, we can make predictions about the future. By extension, we can also make statements about the past. Now, this is not to say that contingency doesn't exist or that some kind of strict uniformitarianism exists, but rather that in the absence of contradictory evidence, the forces of nature are uniform with respect to time and space. One or all of these presuppositions can be false. Indeed, they may even be false in a non-Christian worldview. There may be other supernatural forces that aren't governed by a deity per se, but that is capable of altering matter in some way that is undetectable by us. But this supernatural force would be inaccessible to our intellect. I also want to stress here that someone can hold these views tentatively. For example, many scientists are Christians who likely believe that God intervened at various times in history, such as the resurrection of Jesus. By definition, this is a supernatural event that violates one of the presuppositions of science. But these individuals likely view their scientific work and their spiritual beliefs as separate. That is, epistemic knowledge is achieved differently in questions of natural history of the world and the theological history of God's creation. I've often found that creationists struggle to disentangle these two things. For example, a person could hold the, to me, intellectually honest position that evolution is the scientific answer for the origin of biodiversity, while theologically contending that God created all life. These views can either be held as contrasting knowledge statements. For example, using epistemology X, I conclude Y, while using epistemology A, I conclude B. Even if these technically conflict, one could be agnostic as to which is strictly true in the ontological sense. Alternatively, one could suppose that science is a source of truth and that evolution is really how biodiversity came about, while contending that a creator God dictated the laws of nature with foresight, that they would unfold in such a way that man would emerge. The details of Genesis, in this case, don't matter. Whether from the dust of the earth or the loins of some ancestral ape, original sin is the ultimate point. It is not necessary to have a first human. It is only necessary to have a first human capable of discernment. Now, I'm not a theologian or a Christian, so perhaps it's irresponsible of me to speculate on what sort of views an individual may hold with respect to their own spirituality. My point is simply that humans are capable of holding a multitude of views, and that one can be a creationist while still accepting the scientific answer for the origins of evolution. In this case, you'd simply reject the scientific method as your source of epistemic knowledge. If you're a creationist and you've made it this far, I can only assume you've done so because you're willing to meet scientific claims, such as evolution, on its own turf. That is, you're willing, even if for the sake of argument, to grant the presuppositions of science and evaluate the robustness of the theory itself. With the presuppositions of science out of the way, we can now briefly touch on it as a practical epistemology. Despite what you may have been told, science is not a monolith with a strict methodology. It is a broad system of thought that incorporates a multiplicity of techniques, all aimed at knowledge acquisition. These include empirical methods that may rely on inductive reasoning, as well as mathematical expressions in the forms of theorems and laws that rely on rationalism. Science has also adopted Karl Popper's notion of falsification. That is, to be scientific, a hypothesis must be falsifiable. Indeed, Popper contended that the best theories are those that are so precise in their predictions that they are easily falsified. Vague theories are useless. They can always weasel their way out of contradictory data. Science as a tool is built upon the so-called scientific method, which can be thought of as an avenue for falsification. It works like this. I propose a hypothesis based on some observation or set of observations. I design a way to test my hypothesis, including proposing the sorts of observations that would falsify it. I carry out the test, collect the data, and evaluate the results. If they support my hypothesis, then I make a broader conclusion about the universality of my results. That is, I might speculate on future experiments or results. This forms the basis for future experimentation and is often a forgotten component of science, despite existing in every scientific paper as the discussion section. I also would include caveats about how my methods may not cover all the possibilities, or how there may be an alternative interpretation for the data, including how these other interpretations might be evaluated. Creationists really struggle with the scientific method and appear to think it's quite restrictive in what it's capable of investigating. As an example, the scientific method is absolutely capable of investigating the origin of, say, the eukaryotic cell. If I hypothesize that organelles of the eukaryotic cell emerged via endosymbiosis, then I can formulate a prediction and design an experiment to test this. I might predict that under certain conditions, a larger bacterial cell may phagocytose a smaller, and that occasionally that smaller will persist as an endosymbiont. I would then find a suitable bacterial species known to phagocytose smaller ones, and I would subject them to a series of conditions and observe whether endosymbiosis occurred. If it does, then my hypothesis is supported. Endosymbiosis may have emerged via phagocytosis. Does this mean that it absolutely did, and that the origin of the eukaryotic cell emerged in exactly the way I set up my lab experiment? No, obviously not. That is outside the scope of the hypothesis. I might speculate on how my results relate to the origin of the eukaryotic cell, and I would note that the experiments clearly support this mode of origin as plausible, but I would suggest follow-up studies that could clarify the point further. Also, the general public can be forgiven for being confused on what constitutes a law or a theory in science, because these terms have been used interchangeably and in different contexts for centuries. For our purposes, let's iron out two kinds of theories. These are expressed well in Arlen Stoltzfus's book, Mutation, Randomness, and Evolution. He notes that historically we've used the word theory in two different ways. One is as a conjecture, a proposed explanation of a body of observations that is itself not necessarily proven or even provable. An example of this is cell theory, the conjecture that all of life is composed of cells. It's impossible to observe all living things that have ever existed or ever will exist, and hence cell theory is not provable in a strict sense. In these cases, theories are useful as explanatory frameworks from which hypotheses can be constructed to test additional phenomena. For example, the neutral theory of molecular evolution posits that most standing variation in populations is neutral. Therefore, genetic diversity should scale with population size. If I am studying two populations of damselflies, one of which is known to be more geographically restricted than the other, I might hypothesize, under the framework of neutral theory, that the restricted one will have less genetic diversity than the other. If the data turn out to support this conclusion, then we would state that our hypothesis is supported, and the data that we gathered is evidence of neutral theory. The other kind of theory is abstract and is composed of a series of mathematical proofs and models. These are necessarily true, irrespective of what we find in nature. This is because these abstract theories are consistent with the laws of mathematics and logic. For example, the Hardy-Weinberg equilibrium principle is necessarily true, but it is only empirically true if the system being investigated doesn't violate the assumptions of the principle. In this case, if the population is randomly mating and very large in size, then the allelic dynamics are adequately described by Hardy-Weinberg. Note that these theoretical abstractions are always logically true, but are virtually never empirically true. The philosopher Angela Potocnik calls these idealizations. That is, we construct mathematical models of reality, such as the Hardy-Weinberg principle, that are based upon assumptions that are known to be false. For example, there is no natural population that is infinite, and likely none that is ever truly randomly mating. And yet here we are, applying this theoretical abstraction of reality, knowing that it's false. Why? Potocnik argues that it's because reality is infinitely complex, and that a central goal of science is to understand some component of this complexity, even if it's done little by little. In Judge Holden's words, we are singling out the thread of order from the tapestry. Obviously, there are many individual factors that determine allelic dynamics in populations, far more than we could ever account for in a simple mathematical expression. And yet, we use the Hardy-Weinberg principle all the time, and many populations are well described under its assumptions. We should see that these two definitions of theory are quite distinct, but both are features of the broader theory of evolution. Hence, evolutionary theory is inexorably large, with hundreds of interconnected parts composed of conjectural theories mixed in with abstract theories. Little by little, the goal of the evolutionist is to trim the fat, to dispose of those theories that don't work or have been demonstrated to be false, and to search for ways to unify independent theories across disciplines as a whole, to sort of gain a more holistic view of the origins of biological diversity. I hope this distinction gives you an idea of the complexity of the scientific process itself. Evolutionary theory is an extensive Oedipus. Evolutionary theory is an extensive edifice upon which we formulate hypotheses, and thus the overarching concepts first proposed by Darwin, namely descent with modification, is being tested daily. If this edifice was so flimsy, so ready to collapse as creationists often assert, it would not have been capable of unifying as many disciplines as it has. Before diving into evolutionary theory itself, we should conclude this discussion with what is meant by evidence. The word is often used colloquially to be synonymous with data. For example, the phrase, "we gathered evidence." Evidence is not gathered, it is inferred from data with respect to some hypothesis. Data is agnostic to any theoretical framework we as humans may be operating under, and only becomes evidence if it supports our hypothesis. For example, let's say I hypothesize that organisms who are generalists persist longer in the fossil record than those who are specialist. That is, generalists have lower extinction rates than specialists. What might I do to test this hypothesis? I would likely combine fieldwork at various locations where exist known fossil generalists and specialists across different animal groups, as well as search the literature for additional examples with estimated rates, and then I compile a data set that may be a table in which one column is feeding type, either generalist or specialist, another may be the type of animal, whatever taxonomic level is of relevance, and the third is the persistence in the fossil record. For example, how many distinct layers, at what densities is it found, etc. This is just the data, right? It is not yet evidence for anything. Now, how do I know what I'm looking at is actually evidence for or against my hypothesis? Let's imagine I had a total of 38 species pairs, and in 22 of them, generalists survived longer than specialists, and in 16 of them, the specialist persisted longer than the generalist. From these numbers alone, can I state my hypothesis is supported? No. In fact, if we evaluate the difference using a chi-squared test, we find that our p-value is only 0.42, indicating that being a specialist or a generalist is independent of your persistence in the fossil record. That is, the difference that we found between them, despite the generalist having greater numbers than the specialist, was due to chance alone. Hence, for data to become evidence, we need the following. 1. A hypothesis that can discriminate at least two possible outcomes, and 2. A statistical verification of support. In this way, the concept of evidence is inherently a statistical property of hypothesis testing. This will become important again later when we compare and contrast expectations from evolutionary theory with those from creationism. The conclusion of this portion of the video marks the halfway point. From here, we'll dive into the science, detailing evolutionary theory and how it's a robust explanation for the origin of biological diversity. Is it the only explanation? Nope. Obviously, accounts of creation abound from every religion on the planet, but it is the only scientific explanation. Again, if you reject the presuppositions of science, I hope you've enjoyed the ride up until this point, but nothing from here on out will convince you. We're not playing with the same set of rules. No two individuals are exactly alike. And haploid organisms such as bacteria and archaea that generally reproduce via fission and hence daughter cells are expected to be clones nevertheless differ slightly in their genetic composition. In diploids like ourselves that have two genomes, siblings can differ from one another due to the chance inheritance of different genomic sets. But even in the case that siblings inherit the exact same genomes, they will differ from one another. These differences among individuals constitute variation, and this variation is central to understanding evolutionary theory. Variation can emerge in many ways, either developmentally or environmentally, in which it cannot lead to sustained evolutionary change, or it can emerge from underlying genetic variation. The latter can persist irrespective of development or environment, and hence is capable of fueling evolution. The origin of genetic variation is mutation, and it's the first and arguably the most important mechanism of evolution. Mutation is grossly misunderstood by creationists, so it's perhaps prudent we spend some time explaining it here. First, mutation is often mischaracterized as DNA damage, but that's not correct. Mutations are actually the result of inexact repair. To borrow the analogy from Stoltzfus's book on mutation, imagine a tree falls on your roof and smashes a hole in it. This hole damages the integrity of the roof and would lead to systematic failure of the roof's purpose of keeping your home dry. Often, creationists pitch mutation in this light, as a destructive entity that erodes function. But that's not quite right. Mutations are better thought of as the result of inexact repairing of that hole. This is because mutations occur when polymerase fixes double-stranded breaks, and in repairing the breaks, it might insert different nucleotides than what were there previously. Hence, a mutation is more akin to a repairman that replaces the hole in your roof not with black shingles, like most of your roof has, but with purple shingles. In this way, mutations are not inherently destructive forces. The break itself is destructive, and if not repaired, would likely lead to the death of the cell. But inexact repair is not necessarily harmful. Your roof guards you just fine from water damage, whether the shingles are black or purple. Evolutionary change requires that mutations are capable of generating novelty. Further, we need additional mechanisms that allow that novelty to actually spread and become fixed in the population. The combination of these features, the origination of novelty and its subsequent spread, are the cornerstone of evolutionary theory. The mutational processes that generate novelty are exceptionally well understood. Going back to the 1960s, firm theoretical foundations were laid on how novel genes emerge. One feature of all proteins and non-coding genes are that they often exist in extensive gene families, with dozens of related genes that may differ slightly in their structural composition and function. For example, there are 18 cyclophilin proteins known in humans, each of which carry out similar functions and are involved in mitochondrial metabolism, apoptosis, and inflammation. There are slight differences between each in their structure and in their nucleotide composition of the underlying genes that specify them. The origin of gene families is due to a process called duplication. A single gene is copied and is inserted back into the genome. This can happen in a diversity of ways, including the reinsertion of pre-processed mRNA into the genome via reverse transcriptase. This means that this daughter copy is a descendant of the original, and over time, they will accumulate additional mutations independent of each other. If an additional duplication occurs, either from the parent or the daughter copy, a tree-like structure of relationship emerges between these gene duplicates. Duplication is a well-documented mutational phenomena, but what is the fate of each of these redundant copies? A few things can occur. One is that they can become non-functional pseudogenes. That is, since they are redundant, they are unnecessary, and additional mutational processes can accumulate and disrupt function. We can characterize these non-functional pseudogenes quite readily in the genome because they all share the following features. 1, typically very low levels of transcription and rarely, if ever, translated. 2, they lack an open reading frame. 3, they lack a dedicated promoter. Or 4, they are truncated relative to the parental gene. For example, they have a premature stop codon that renders the resultant mRNA chain far too short to form a functional product. Around 5% of the human genome is made up of pseudogenes. This number has been slowly climbing ever since the publication of the Human Genome Project in 2004. Another possibility are these genes undergo subfunctionalization. This process is likely key to understanding the origin of genomic complexity. Since there are now 2 copies of the same gene, each are free to compensate any loss of function mutation in the other. In this way, they become conditionally dependent, and 2 genes are now necessary to perform the function that one did prior to the duplication. See my video on the evolution of genomic complexity for an explanation on the importance of subfunctionalization in evolving complex interaction networks. Lastly, the duplicate can undergo neo-functionalization. That is, it acquires a novel function that did not exist in the parental copy. One reason this occurs is that the redundant copy is free to mutate in any direction, and while this often leads to loss of function, it will occasionally result in novel bindings or catalytic capacities that convey a benefit to the cell. We have extensive examples of this. For example, Asis and Bactrog in 2013 published a comparative study of new gene duplicates between two species of Drosophila, Melanogaster and Pseudoobscura. They found dozens of novel protein-protein interactions between young gene duplicate products relative to their parental copies, and that the older the daughter copy, the more widely expressed it was across tissue types. Neo-functionalization is the process by which mutations add new information, a feat that creationists often assert is impossible. Further, these do not occur because of so-called reductive evolution. Nothing is lost, and the original function of the gene is retained. Instead, a novel function has emerged from a redundant copy following duplication. Therefore, mutational processes meet the burden of generating novelty. And this is only one mechanism at their disposal. We have extensive evidence of de novo gene origin from non-coding sequences due to the chance acquisition of an open reading frame, as well as horizontal gene transfer. Transposons, typically parasitic DNA elements, also exist as standing variation in all natural populations that are capable of being co-opted by the host genome. Creationists tend to shift the goalpost here, suggesting that perhaps mutation can do small things, but aren't capable of generating large-scale variation, such as the origin of novel body plans. This claim has always been surprising to me, given the findings of the field from evolutionary developmental biology, so-called Evo-Devo, going back to the 1980s. By mapping genes responsible for the ordering of organismal body plans, we found that there is only a handful of them, and that slight changes in their expression levels can lead to dramatic differences in phenotype. So much so that early embryologists, by shifting expression timing, managed to alter the development of a fruit fly such that it grew legs out of its head. Such simple tinkering indicates that there is incredible creative capacity in the hands of mutation. Generating novelty is half the puzzle. For a coherent theory of evolution to be capable of explaining diversity, that novelty needs to persist and spread to all members of the population. How does this occur? One way is by dumb luck. The preacher of Ecclesiastes was the first to hit upon this concept, writing, "I returned and saw under the sun that the race is not to the swift, nor the battle to the strong, neither yet bread to the wise, nor yet riches to men of understanding, nor yet favor to men of skill. But time and chance happeneth to them all." All breeding populations are finite, and every generation only some individuals will reproduce, not necessarily because they harbor genetic variation that made them less likely to find mates, but because lightning struck a tree and fell on them, or they got eaten by a tiger. In the case of diploids, they only pass on half of their genomic content, and so even getting to reproduce doesn't guarantee all the variation in the population persists each generation. In this way, for every variant that is lost by chance, the alternate allele is fixed. When an allele fixes in a population, this means that all the individuals in that present population are descendants of the individual in which that allele first emerged. We call this individual the last common ancestor, or the coalescent ancestor, and there is extensive mathematical theory to calculate the probability distribution of the time we should have to wait until this individual is reached, which is a feature of the size of the population and the mating structure. This also means that any variation that exists in the population has emerged along the lineages since that ancestor. That is, all populations have a tree-like structure with some coalescent ancestor. That coalescent ancestor, importantly, while technically an individual, is better thought of as a genome. When coalescence occurs, we are stating that all the genomes in the population descend from that one ancestral genome. But remember, in diploids we have two genomes, and hence only one of the genomes of the coalescent ancestor is the actual ancestor genome. That individual's other genome is lost by chance. This is an important point, and it strikes at the heart of the creationist claim of created heterozygosity. This is the conception that there is too much genetic diversity present in modern populations for them to have undergone a recent bottleneck some 4,000 years ago, and hence all organisms must have been created with extensive genetic diversity. The flaws in this are blatantly obvious when we understand coalescence. All creationists would accept that modern populations have some single coalescent ancestor, but they fail to recognize that that ancestor is actually just a haploid genome. Haploid genomes have no diversity. Only diploid individuals can have diversity. Hence, all genetic variation in any population emerged since the time from that ancestor via mutation, which indicates created heterozygosity cannot rescue them from the fact that to account for modern levels of heterozygosity, they need incredibly rapid mutation over the past 4,000 years at rates far exceeding anything ever observed. The chance loss or fixation of alleles is called genetic drift. At the molecular level, genetic drift is an incredibly important source of allelic frequency fluctuations. It also acts in opposition to the next major source of novelty spread, natural selection. Selection is more complicated than these other mechanisms of evolution due to the fact that it is an emergent property of fitness. Fitness can be defined in a range of ways depending on the scale of focus. That is, an allele, genotype, phenotype, or individual can be thought of as having fitness. An individual's fitness is simply the number of offspring they have relative to some population average. That is, fitness is defined by fecundity. We could also define it as the survival probability of an individual of a given age class relative to other members of that age class. This is a fitness defined by viability. There are subtle differences mathematically in how these influence allele frequencies that are well understood in population genetic theory. For our purposes, we need to understand that differential fitness alone is not sufficient for evolutionary change. An individual can have more offspring than other members of the population by chance alone. If we measured their fitness, it'd be higher than the average, but there's no evolutionary response to this differential fitness if it's not the result of that individual's genotype. But let's say an individual that possesses some genotype has more offspring than the average member of the population because that genotype grants them some phenotypic advantage. In this way, an individual's offspring inherit that genotype, and hence the phenotype it codes for, and themselves go on to have more offspring as well. Over time, the novelty sweeps through the population. Both genetic drift and natural selection are understood theoretically and empirically. Countless studies have been performed over the past century since they were proposed that demonstrated these processes are capable of altering the genetic landscape of populations. Two laboratory experiments are instructive to demonstrate not only these forces in action, but how well theoretical population genetics can predict the data. Fruit flies, specifically the species Drosophila melanogaster, has long been a model system of genetic studies. In 1942, Teissier studied a lab population of fruit flies that were polymorphic for the allele CY called curlywings. In individuals with genotype CY, they die as embryos, whereas CY+, where the plus is the wild-type allele, have half the fitness of the homozygous wild-type individuals. The lab population began with 1/3 wild-type and 2/3 curly-wing alleles. We can predict the frequency of the curly-wing allele in each generation as follows. P' as the frequency of the curly-wing allele in the next generation is equal to the frequency of the homozygotes in the preceding generation, which is P², multiplied by the fitness of the homozygous curly-wing individuals. Now remember, since those are lethal, that fitness value is 0. plus the frequency of the heterozygotes multiplied by the heterozygote frequency divided by all the possible genotypes and their fitness. The results of the study are plotted here. The black dots are the empirical allele frequencies, and the black line is the theoretical expectation given the equation I just walked us through. The fit is quite remarkable. This indicates that using the principles of Mendelian inheritance and natural selection, we were able to predict genotype frequencies into the future. A similar feat is capable with genetic drift. Since genetic drift is the chance fluctuation of alleles for a biallelic system, it is not strictly possible to predict a priori which will become fixed and which will be lost. Instead, we can only make probability statements. However, with enough replicate populations, we can test whether our intuitions are valid. Imagine a population with two loci, big A and little a, at a frequency P and Q. Assuming their frequencies drift each generation by chance, we can exactly calculate the probabilities using the binomial expansion showed here, where I is the number of copies of the A allele in the next generation, and N is the size of the population. The exclamation mark indicates a factorial, so if I is equal to 3, then I factorial equals 3 times 3 minus 1 times 2 minus 1. Obviously, this way of calculation becomes unwieldy if I is large, but the probability is exact. Often in population genetics, we use diffusion approximations, which kind of give a close enough answer and are far more tractable. With this in mind, let's review a groundbreaking study from 1956 by Bury. They started with 107 replicate populations initiated by 16 heterozygous flies for the brown eye locus called BW. Hence, the starting allele frequency was 50%. After 18 generations, nearly half the populations are fixed for the brown eye allele, the other half are fixed for the wild type, with a few still polymorphic. Shown here is the theoretical expectation using the binomial expansion, and the other is the empirical data. Notice that despite genetic drift being a stochastic process, given that we understand the mode of inheritance and the starting frequencies of the alleles, we can very accurately capture the dynamics of the population. In 2019, an incredible study was published in PNAS that combined all of these theoretical principles with a fully pedigreed natural population of Florida scrub jays. This work was led by Nancy Chin at the University of Rochester, and they were able to tease apart fluctuations in allele frequencies due to genetic drift from those driven by natural selection. The study took advantage of several decades of work on this small natural population in which volunteers went out, banded birds, tracked their matings, and all of their offspring. They also collected tissue samples from all the individuals and were able to sequence across multiple generations. Remarkably, they found that their theoretical models were exceptional fits to the observed allele frequency changes over time, as indicated by most of the points shown here falling along the 1-to-1 line in the graph. Another way to visualize this is here, in which the blue line is the observed and the black is the simulated under this mathematical model, with the gray outline being the 95% confidence interval. Notice that the observed falls within this interval across decades. Using their model, they were able to identify a number of mutations that were significantly higher in representation than expected under genetic drift alone, indicating that these were being swept through the population by positive natural selection. A few key points are worth summarizing here. In this section, we've established the following. 1, that novelty emerges via mutation, and that we have extensive empirical examples of mutations generating new phenotypes. 2, that genetic drift and natural selection as mechanisms for causing novelty to spread through populations have strong theoretical and empirical support. And 3, that we can integrate all of these processes together to examine a natural population, and that our models that work well on paper and in the lab also excel in nature. Thus, we've developed a foundation for how evolutionary change occurs. For the final chapter in this video, let's expand this beyond the confines of populations to the origins of genera, families, orders, and phyla. The evolutionary biologist and architect of the modern synthesis, Ernst Mayr, once remarked that while evolution is a continuous process, the origin of species is itself the evolution of discontinuities. That is, if we have two distinct species that are incapable of reproducing and produce fertile offspring, these are clearly discontinuous units of biology. And yet, evolution posits that their ancestors were capable of interbreeding. If evolution is continuous, how does it give rise to something seemingly so discontinuous? This confusing fact has befuddled many a creationist through the years. It has led them to make bizarre statements like, if humans evolved from monkeys, why are there still monkeys? And cows always give birth to cows. Richard Dawkins in The Ancestor's Tale refers to this as a kind of tyranny of the discontinuous mind. To understand speciation, and more broadly macroevolution, we need to understand how continuous evolutionary processes, like those discussed previously, generate discontinuous biological diversity. Let's begin with an analogy. If you're watching this video, chances are you speak English. The English language is itself a conglomerate of local languages in Britain that emerged first in the Anglo-Saxon era prior to the Norman invasion in 1066, and afterward was altered by Norman influence. You can thank them for words like facade. One of the earliest Anglo-Saxon texts, copied by monks between 700 and 1000 AD, is the epic poem Beowulf. Shown here is an excerpt from the text. Despite being written in English, no modern English speaker can read it. Jump forward to 1100 AD, following the Norman conquest, the language began to change. New words were adopted, and the structure of sentences started to alter. Shown here is from Sir Gawain and the Green Knight, written in the 1300s. A classic tale of surviving a beheading, this Arthurian legend is almost readable. There are recognizable words, but the structure is odd and the spelling is weird. By the late 1500s, we have William Shakespeare, who no doubt contributed to much suffering in your English literature class. Despite his work being considered modern English, I'm sure many of you still struggled to grok meaning from his work. For example, in the classic play Hamlet, Polonius tells Ophelia, "We are to blame in this, 'tis much proved, that by devotion's visage and pious action we do sugar o'er the devil himself." All the words are known, but the delivery is odd, and many won't understand what Polonius here is saying, even if they know the words themselves. For the record, he's remarking on the fact that we often hide our sins behind piousness. It's a statement about hypocrisy. Languages are often thought to evolve. Clearly, English has changed over time in the 1,000 years since it was first spoken. While language change is not an exact analogy to genetic change, it is an instructive one. Children speak the language of their parents, but often slightly different, influenced by new varieties of words and structures that emerge among their peers and their community. Sometimes these quirks of language spread beyond the local community, probably far more are lost. But no parent failed to understand their child, and no child failed to understand their children, etc. And yet, taking a step back, we clearly see that language is not the same, so much so that we designate it into these discrete categories: Old, Middle, and Modern English. And yet at no point in history did a parent speaking Old English give birth to a child who spoke Middle English. The change in the language system every generation was ever so slight as to be imperceptible in the moment. This is not to say there weren't periods of rapid change, such as with the Norman conquest, but the rapidity was never such that parents literally couldn't understand their children. Here, rapid is relative to the average pace at which a language changes. This analogy fairly well captures evolutionary dynamics. We can expand this to divergence between languages. For example, both French and Spanish descend from a Latin root, and yet over time these have diverged such that today they can't understand each other. But at no one point in time did a Latin-speaking parent give birth to a French-speaking child. The change was gradual and continuous, and yet, to Mayr's point, it led to discontinuity. French and Spanish are distinct languages. In the previous section, we showed that there exist evolutionary processes capable of changing populations in the Old English to Modern English way. But can these same processes actually increase biological diversity? That is, can an ancestral population become separated and diverge into two new, distinct species? In general, there are two components to speciation, the process of an ancestral population diverging into two separate species. These are, 1, the cessation of gene flow, and 2, the accumulation of reproductive barriers. While speciation can occur in sympatry, that is, in the same area in the face of gene flow, it is far rarer, and most often speciation occurs via allopatry, that is, between geographically isolated subpopulations. While these barriers are often described as being large, like a river or a mountain range, they need be either large nor complete. Sewell Wright showed that significant population divergence can occur if less than one migrant per generation is exchanged between populations. Barriers to gene flow that have been identified in natural populations are diverse. A famous example is the emergence of the Florida Peninsula, which separates many sister taxa between the Atlantic and the Gulf of Mexico. This separation occurs because the peninsula stretches into the tropics, while the northern Gulf and the Atlantic are in the temperate zone. Hence, species that are adapted to temperate climates don't traverse the tropic waters. The emergence of this peninsula has been studied extensively in comparative phylogeography, spearheaded by John Avis, who found over a dozen taxa that show similar divergence patterns separated on either side of the peninsula. To give a personal example, I examined divergence patterns in hosteriid amphipods in the Gulf of Mexico, these small crustaceans that live on sandy beaches. There's half a dozen or so species in the Gulf, and I compared patterns of relatedness on either side of the Mississippi River between two genera with species distributed east and west of the river. I found that the amount of divergence between the two genera actually overlapped, and that it corresponded to a time in the Gulf's history when there was a massive sedimentation event that was occurring down the river. Thus, the same geological event explains the degrees of divergence between two independent taxa in the Gulf. No creationist doubts that barriers to gene flow can emerge, but can reproductive isolation result, and how does it occur? Importantly, barriers to gene flow aren't enough. Given enough time, separated populations will come back into contact, and if they can reproduce and have fertile offspring, they will homogenize. Reproductive isolation reinforces the separation between them, even if the initial barriers are removed. The genetics of reproductive isolation began with the pioneering evolutionary biologist Theodosius Dobzhansky and his students. Groundbreaking work was done by Jerry Coyne and his graduate student Alan Orr in the 1980s, all working with Drosophila. This work provided numerous mechanisms for the emergence of reproductive isolation, but one of the most widespread is called Bateson-Dobzhansky-Mueller incompatibilities, or BDMIs. Imagine an ancestral population that is split by some geographic barrier. Over time, novel mutations emerge in each of these populations. Since gene flow is limited or absent, the variation isn't shared between them, and they can fix in their respective populations via genetic drift or natural selection. When the two populations come back into contact, these fixed differences between them interact with one another negatively. One famous example is the BDMI between several species of pisciliid fish called the swordtail fish in the genus Xiphophorus. Studies have found that alleles in the gene RABD3D interact in hybrids to cause melanoma. Hence, hybrids between these populations have reduced fitness, which buffers the parental populations against the homogenizing effects of gene flow. In 1989, Coyne and Orr published a seminal paper on the patterns of speciation in Drosophila that showed that reproductive isolation was a function of the genetic distance between species. This pattern is exactly what is expected if BDMIs are prime drivers of reproductive isolation. It also shows, importantly, that speciation is a continuous process. It occurs gradually via the accumulation of genetic differences between isolated populations. This has important implications for the creationist claim that rapid speciation occurred after the Noahic flood a mere 4,000 years ago. They often designate the level of the kind at the family level, but when pressed, I found that kind can mean anything from genus to phylum. Irrespective of definitional squishiness, the known mechanisms of speciation, that is, the accumulation of BDMIs, are gradual and mostly driven by genetic drift. Unlike natural selection, genetic drift is slow. Its pace is dictated by the population size. For organisms with large populations, it can take thousands, if not millions, of generations for sufficient divergence to accumulate. The 4,000-year timeline proposed by young Earth creationists is simply too restrictive to permit speciation to occur at a rate necessary to explain modern biodiversity. And importantly, these BDMIs could not have been segregating ancestrally. If they had, then any time the two homozygous alleles came into contact, natural selection would purge them from the population. Hence, these BDMIs must have emerged since those populations diverged from one another as de novo mutations. We've now seen that speciation can occur and proposed a mechanism for it that relies on the evolutionary processes of populations, that is, mutation, genetic drift, and natural selection. Thus, evolutionary theory is well equipped at explaining the emergence of biological diversity. What's left to argue about? Some creationists would contend that all that's been discussed thus far falls within their worldview and is merely microevolution, which they have arbitrarily extended to include the origin of species as well, instead of its historic usage in population biology. To be clear, this is perhaps one of the most impressive goalpost shifts in all history. The original creationists, like William Paley, would roll over in their grave at some of the evolutionary ideas that creationists now accept, including the mutability of species or rapid speciation. The rejection of macroevolution at whatever arbitrary boundary they designate that is convenient for them is an appeal to a kind of last Thursdayism. That is, shared genetic variation reflects ancestry until last Thursday, at which point all appearance of ancestry is illusory. To make this claim, they must assume that the laws of Mendelian inheritance are arbitrary, and that they stopped working at some point in the past, that there existed an individual who possessed variation that was not inherited, but rather emerged de novo via divine intervention. What this means is that there are living individuals of the same species that have no direct ancestry with one another. Their lineages have independent created origins. What's the evidence for this? None. This is a religious assertion, which brings us back to the presupposition discussion we had previously. For an explanation to be scientific and worthy of scientific discourse, it must conform to the presuppositions of science, i.e., it must be a natural explanation built on known observed forces, and it must be falsifiable. Last Thursdayism is an infamously non-falsifiable proposition, and that is exactly what common design is. While I contend this sort of ideology is intellectually stunting, even if contained within Sunday schools, it has nevertheless mounted consistent attacks on the public education system. Creationism, in its various forms, has repeatedly tried to be part of the scientific, not merely the theological, discourse, to promote itself as worthy of being taught in biology classrooms. What mechanisms would be taught exactly? How would a teacher explain to their students what a kind is? How would they delineate whether ancestry stops last Thursday or a billion years ago? Alternatively, evolutionary theory possesses exquisite explanatory power. If we reject last Thursdayism, as we should, and follow the evidence accepting that the laws of Mendelian inheritance aren't arbitrary and that evolutionary processes that we've discovered act the same in the past as they do today, then the disparate features of biological systems are immediately united. Macroevolutionary studies rely on a range of data types, but three remarkable sources that consistently corroborate one another is molecular divergence, strata of fossil occurrence, and radiometric dating of the strata itself. For example, the level of molecular divergence among all arthropods suggests a Precambrian origin of around 600 million years ago, and that most orders radiated in the Cambrian some 500 million years ago, assuming a relatively constant molecular clock. When we look into the fossil record, we find many of the major arthropod groups emerged during the Cambrian, as expected by molecular dating. This alone is a remarkable correspondence, but to add to this, when we radiometrically date Cambrian rock, the ages inferred are in the range of 485 to 541 million years ago. A creationist would contend that each of these dates are arbitrary, that molecular dating and radiometric dating are meaningless, and that the Noahic flood explains fossil distributions. If that were true, there would be no expectation of a correspondence between each of these values, and yet, remarkably, they overlap completely. This same pattern is seen across the tree of life. The level of genetic divergence between modern taxa is predictable from the timing of their occurrence in the fossil record. This fact was first demonstrated over 50 years ago by the remarkable linear relationship found when comparing divergence of protein allozymes across vertebrates with their proposed divergence from the fossil record. If the fossil record is truly an arbitrary source that is not a record, as the despicable Kent Hovind likes to claim, then there is no reason that it should so accurately predict the degree of genetic divergence between taxa. These correspondences are also direct tests of macroevolution. If we failed to ever find a correspondence between molecules and fossils, then macroevolution would be falsified. If radiometric dating failed to correspond with the proposed origins of major animal groups, then macroevolution would be falsified. If the occurrences of fossils in the geological column occurred long before they are expected to have diverged based on molecular data, for example, the finding of a rabbit in the Precambrian would immediately falsify macroevolution. Last Thursdayism, or common design if you want, is immune from such tests because it does not make any predictions that can be falsified. Any data can be construed to fit it because it is not a coherent theory. It is a reactionary ideology founded on the rejection of the scientific method. Any feature can be explained under this framework. Shared homology? God did it. Differences between organisms? God did it. Anything can be explained under last Thursdayism. We shouldn't close out our discussion of the origin of species without mentioning our own evolution. It is this subject that creationists are the prickliest. They are more than willing to permit all arthropods share a common ancestor, despite the inordinate amount of genetic diversity they'd need to account for in a measly 4,000 years, but humans and chimps must be distinct. To be clear, humans and chimps are far more similar than any two arthropods, even closely related ones. Many arthropods have more genetic diversity within populations than humans and chimps have divergence between them. The closest extant species to humans are chimps and bonobos. In fact, since chimps and bonobos are sister taxa themselves, the level of divergence between humans and chimps is approximately the same as between humans and bonobos. We diverged from the chimpanzee plus bonobo lineage around 6 to 8 million years ago, and we all diverged from gorillas between 8 and 10 million years ago. These dates are supported by two key facts. One, the fossil record, which indicates the last chimp-human ancestor may have been a relative of Brachiopithecus or Sahelanthropus, each of which lived around 7 million years ago, and two, molecular dating, which corresponds to the divergences within this window. No human fossil has ever been found and dated at this age range. The molecular evidence supporting the relationships between chimps, humans, and gorillas is striking. While creationists often contend that genetic similarity is merely common design, as already discussed, the best support for this relationship actually comes from the discordance, not the concordance. Let me explain. Due to recombination, genomes are mosaics of ancestry, with each haploblock having a unique ancestor that lived at a different time and place than some neighboring block. When examined at the species level, this means that some patterns of ancestry in those blocks are discordant with one another. Theory predicts that most of these haploblocks should correspond to what we call the species tree, the true relationship between species. In this case, they should show that humans and chimps are more related, with gorillas as an outgroup. But if common ancestry is true, a proportion of the gene tree topologies should not match this. Instead, they will show that humans and gorillas are more related, or chimps and gorillas are sister, with humans as the outgroup. That is, each of the three possible topologies will be present across the genome. In an evolutionary framework, the only way for these alternate topologies to exist is if coalescence did not occur during the interval in which humans and chimps were joined into an ancestral population, instead occurring deeper when gorillas, chimps, and humans were all in a common ancestral population. We call this incomplete lineage sorting, or sometimes deep coalescence. When this occurs, the probability that coalescence happens between a lineage that would eventually lead to humans versus chimps or gorillas is completely random. That is, the alternate topologies should be equal to one another in frequency. After all, in a common ancestral population, all individuals are mating freely. They have no foresight into which lineage will eventually lead to humans, chimps, or gorillas. Ebersberger and colleagues in 2007 examined gene tree distributions for human, chimp, and gorilla species tree and found that 76% of the gene trees across the genome matched the species tree, while 10.42% showed chimps and gorillas as sister with humans as an outgroup, and 10.17% show human and gorilla with chimp as an outgroup. A similar study by Caswell and friends in 2008 looked for gene tree concordance between humans, chimps, and bonobos. They found a remarkable correspondence between the expected levels of gene tree discordance given divergence time between humans, chimps, and bonobos, and the observed discordances. Again, remember, this correspondence is only expected under common descent. If humans and chimps don't actually share common ancestry, then there is no mechanism that should generate almost exactly equal levels of discordance across each possible topology. While genetic evidence tends to be limiting from fossils, we do have genomes from two extinct hominid species, Neanderthals and Denisovans. While there is evidence of introgression between ourselves, Neanderthals, and Denisovans, for most of the genome we find that we diverge from Neanderthals around 550,000 years ago, and from Denisovans between 600 and 750,000 years ago. This is corroborated by both the fossil record, which suggests that our lineages converged into either Homo heidelbergensis itself or a close relative, as well as molecular dating that corroborates a heidelbergensis-like coalescent time. That is, if creationists want to include Neanderthals and Denisovans as bona fide Homo sapiens, it will result in a more than doubling of the amount of genetic diversity within the human lineage. This would require pushing back the coalescent ancestor of all humans to nearly 1 million years ago to account for this genetic diversity, because remember, all diversity in a modern population must have emerged since the last common ancestor of that population. Thus, in regard to the evolution of humans, we have an extensive fossil record stretching back to the last ancestor of humans and chimps that captures each of the major transitions, from increasing brain case size to bipedalism, as well as genetic evidence of two distinct hominid species that diverge from us deeper than the last common ancestor of all Homo sapiens. Furthermore, we find that patterns of gene tree discordance are only predictable assuming a model of common descent and are inexplicable under common design. Fucking rain, man. we have now spanned the evolutionary narrative, from first principles of population genetic theory derived from Mendelian inheritance, the nature of mutations as the source of novelty, to how that novelty spreads through populations. We saw that populations can become divided and accrue reproductive isolating barriers, but that these occur slowly, and that it's very unlikely that they could occur in a biblical timeline relying on known mechanisms. We then saw that there is a remarkable concordance between fossil estimated divergence times and genetic divergences, and that these are corroborated by radiometric dating. Lastly, we saw that human evolution is strongly supported by molecular phylogenetics and the fossil record. As long as this video is, I have barely scratched the surface. The most difficult part for me was in deciding what to leave out. But the joy of making this content is that little by little, I can create videos that touch on some aspect of evolutionary theory here not discussed. In addition, since this was meant to be a celebration of the channel and reaching 1,000 subs, I spent considerable time in the beginning on my own personal story, which I hope you found added to the experience. I want to thank you all again for your support this past year and for helping the channel grow. I want to conclude here with some final thoughts on the future of the channel. In the short term, you can expect the usual sort of content focused on evolution education and pseudoscience debunking, with a sprinkling here and there of the history of science. In the longer term, one suggestion was to consider doing book reviews of popular evolutionary books. These would probably only be focused on pop science books instead of technical books, so that I'd be covering things you might actually read or be interested in reading. If that's something that you'd find interesting, let me know in the comments. Another thing that's still in the works, yes, Ian Chen, I haven't forgotten you, is my large-scale documentary project that's tentatively titled Demystifying Evolution. The initial fieldwork and filming is complete, but now the lab work is underway. Once the lab work is completed, the sequencing effort itself begins, and then we can start the grueling process of analyzing the data and writing up the manuscript. So the conclusion of this project is still quite a ways away, I'm afraid to say. Thus is the nature of science. I have toyed with the idea of releasing bits and pieces as shorts, like little updates, but I worry that these won't get very many views and so probably won't be worth the effort, and that they will be spoilers for the final thing. So, I don't know, let me know in the comments if you have a preference. Thank you all again for your support, for liking, commenting, and subscribing, and continuing to engage with me on this great subject that is evolutionary biology. I hope you found this special interesting, and that you've learned something both about me and about science and evolution in general. After all, as someone rather famous once said, there is grandeur in this view of life. Catch you all next time.